Is quantification of a rotating body's radius, mass, and speed distribution around a rotation axis. So you need to have a rotating body, and in addition to that, that rotating body has to have radius and mass distribution around a rotation axis. So let's take a look at an example of a body that has angular momentum. Here we've got a black ball of mass m, so it has mass. That mass is located a distance r away from this rotation axis. So it has a mass and radius distribution around a rotation axis. And the last thing you need to have is it has to have a speed. It can't be sitting there. Notice this object is moving around this rotation axis. So you have three ingredients. It's got a mass. That mass is distributed at a radius away from the rotation axis, and the object is moving around the rotation axis. Since it's got all three ingredients, the object has angular momentum. Now, an object doesn't necessarily have to be located away from the rotation axis to have angular momentum. A good example of this would be an ice skater. An ice skater also has angular momentum. Notice the ice skater is spinning around her own rotation axis. She's got a mass. That mass is distributed away from the rotation axis, and she has a speed or rotation around this rotation axis. She's got her three ingredients. She's got mass, she's got a rotation, so she's moving, she's got speed, and she has a distribution of that mass away from the rotation axis. So what do I mean by that is, notice she starts out with her knee sticking out and her elbow sticking out. Then she changes that by pulling her knee in, and she extends her arms upward. Since she's distributing her mass around this rotation axis, she has angular momentum, and she is also changing her angular momentum by increasing her speed around the rotation axis. Both the ice skater rotating around a rotation axis and this black ball rotating or orbiting around this rotation axis, both of them have angular momentum.